Okay, now in the previous lecture we discussed about the zeroth law of thermodynamics. Zeroth law of thermodynamics. In the definition of zeroth law, we have seen that when two systems A and B are in separately thermal equilibrium with a third system, then these two systems A and B are in thermal equilibrium with each other. Also, we mentioned that the zeroth law of thermodynamics actually establishes the basis for the concept of temperature. Basis for the temperature. So in this lecture we will discuss how we can establish the concept of temperature by using the zeroth law of thermodynamics. In anthropomorphic meaning or understanding, you know that the temperature is a measure of hotness of a macroscopic object as felt by the human body. So temperature is the hotness of a macroscopic object as felt by the human body is the meaning in the anthropomorphic understanding. And similarly, the coldness actually is the state of less hotness. So these are the common things which we will usually use for the temperature. But a scientific understanding of the concept of temperature builds upon thermal equilibrium established in the zeroth law of thermodynamics. For that, to get a scientific understanding of temperature or the actual concept of temperature, consider two systems A and B. The system A is in the state characterized by the thermodynamic coordinates say x1, y1, which is in thermal equilibrium with the second system B, which is in the state x1 prime, y1 prime. Now the system A is removed and its state changed. There will be found a second state of the system A characterized by the parameters x2, y2. Suppose that is in thermal equilibrium with the system B in the state x1 prime, y1 prime itself. That means if you are having two systems A and B and they are separated by a diathermic wall, definitely they will be in thermal equilibrium, and the system A is having the state x1, y1 and the system B is having the state x1 prime and y1 prime. Now the system A is removed and it will undergo some changes and its state has been changed to new state and is characterized by x2 and y2. Now if you consider the system B which is in the same state x1 prime, y1 prime, then the state A of the system, the state characterized by x2, y2 of the system A is in thermal equilibrium with a state x1 prime y1 prime of the system B, then this x1 y1 state A of A will be in the thermal equilibrium state of the another state of the same system characterized by the coordinates x2 and y2. Then the experiment shows that there exists a set of states x1 y1, x2 y2, x3 y3 and so on is in thermal equilibrium with x1 prime y1 prime of B, and all of which by zeroth law are in thermal equilibrium with one another. We shall suppose that all such states, when plotted on a xy diagram, lie on a curve and which we shall call an isotherm. So what we are going to define is, if you are having a system A which is characterized by the state x1 y1 which is in thermal equilibrium with another system characterized by the state x1 prime y1 prime, then experiment shows that A can have the states x1 y1, x2 y2, x3 y3, etc., which is in thermal equilibrium with the state B having the parameters x1 prime y1 prime. Then according to zeroth law, each state of this system A is in thermal equilibrium with one another. Now if we plot the points x1 y1, x2 y2, x3 y3 on a diagram, on a xy diagram, here I am considering this as x coordinate and this as y coordinates, then the locus of all points lie along a curve like this. Here it will be x1 y1, here it is x2 y2, x3 y3, x4 y4 and so on, and this curve is called isotherm. So an isotherm is the locus of all points representing states in which a system is in thermal equilibrium with one state of another system. So isotherm is the locus of all points representing states in which a system is in thermal equilibrium with one state of another system. If the experiments are repeated with different starting conditions, another set of states of the system A lying on another curve may be found. That is, if you start with another set of initial conditions, then another set of states of the system A lying on another curve may be found, every one of which is in thermal equilibrium. That means if you repeat the same experiment with different starting conditions, here we have started with the state having the parameters x1 y1 is in thermal equilibrium with x1 prime y1 prime. Now if you start with another, the state system A is having some other state which is we can represent small x1 y1 is another set of parameters, then is in thermal equilibrium with the system B with x1 prime y1 prime, and this system A is having the parameters x2 y2 x3 y3. All these states are in thermal equilibrium with the state x1 prime y1 prime of the system B. Then the states x1 y1 x2 y2 x3 y3 etc. of the system A are in thermal equilibrium. Then the locus of all points of the system A characterized by the different states x1 y1 x2 y2 x3 y3 etc. will lie on another curve which is again another isotherm. Now all states of corresponding isotherms of all systems have something in common, namely that they are in thermal equilibrium with one another. In these states, that is the states of the system which are in thermal equilibrium, the system may be said to possess a property that ensures their being in thermal equilibrium with one another. We call this property as temperature. That is, for a particular isotherm, if you consider this isotherm, this is having some property of this system is in common for the states x1 y1 x2 y2 x3 y3 x4 y4 etc. Or for this isotherm, the different states x1 y1 x2 y2 x3 y3 etc. of the system have something in common, and that property which is common to all states of the system in thermal equilibrium is called the temperature. So here we can define the temperature as the property of a system which is common to all states of the system in thermal equilibrium with each other. That is, property common to all states of a system in thermal equilibrium, or remember that these states are in thermal equilibrium. So this is a property of the system, or the temperature of a system is a property that determines whether or not a system is in thermal equilibrium with other systems. So this determines the whether a system is in thermal equilibrium or not. That is, the equation of state. Equation of state means it is the relationship between the thermodynamic variables of a system. So if you consider x and y are the thermodynamic variables of a system, then the equation of state of the system can be written in the form the function of x and y is equal to some constant, because for the state x1, y1, x2, y2, x3, y3 of system A, which are in thermal equilibrium states, then I have a common property, or the property is common to all states, equilibrium states of the system, then that is a constant. We can write the equation of state in this way: the phi of xy is equal to c. This several combinations of x, y and y can be found for a third constant parameter c. For example, to get an idea of this one, consider we have several gaseous systems in thermal equilibrium with each other. Or consider a gaseous system A which is having different states which are in thermal equilibrium with each other. It is characterized by the different pressure and volume. Let's say P1 V1, P2 V2, P3 V3, etc. Then we can write phi of the function of P1 V1 is equal to phi 1 of phi 2 of P2 V2 is equal to phi 3 of P3 V3, etc. That is, phi 1 of P1 V1 represents the equation of state of the system A when the pressure is P1 and the volume is V1. And phi 2 of P2 V2 represents the equation of state for the system A when pressure is P2 and the volume is V2. And phi 3 of P3 V3 represents the equation of the same system A with pressure P3 and volume V3 and so on. Then if these states, that is the pressure P1 and volume V1, and another state characterized by the pressure P2 and volume V2 and pressure P3, volume V3 are in thermal equilibrium with each other, then these equational states are equal, and which is equal to a common property of the system, and that common property is called the temperature. So this is the concept of temperature which we can draw from the zeroth law of thermodynamics and the thermal equilibrium conditions. Thus the numerical value of each of these functions is same and define the temperature. This is the property of a thermodynamic system that is responsible for thermal equilibrium. Now if you consider two systems such that phi 1 of P1 V1, this is a system, and the equational state of another system is phi 2 of P2 V2 are not equal, that is they are not in thermal equilibrium, then there will be a net flux of energy from one system to another till the two attain the same temperature. That is, if you consider two systems A and system B, the A is in the state characterized by P1 V1 and B is in the state characterized by P2 V2, and they are separated by a diathermic wall, and if these two systems are not in thermal equilibrium, then there will be a net flow of energy from one system to another till the two attains the same temperature. The flux of energy responsible for thermal equilibrium is the thermal energy or heat energy. So if the temperature of the system A and the temperature of the system B, when the system is in the state characterized by the pressure and volume P1 V1 and that by B is P2 V2, then there is a net flow of energy between the system A and system B, and this energy is the thermal energy or heat energy. So now we can conclude that heat flows from a higher numerical value of the function to the lower value. That is, the numerical value is nothing but the temperature. If Ta is greater than Tb, the temperature of the system A is greater than temperature of the system B, then there is a flow of heat energy from the system A to the system B. Now what we can say is that the heat always flows from a higher numerical value of the function to a lower value. The difference in the two values are the temperature difference. This temperature is the level for the thermal intensity and is a key factor in determining the direction of flow of heat. So this is what we can conclude about the temperature. Temperature is actually a property common to all states of a system in thermal equilibrium, or we can define this way: property common to all states they are in all systems they are in thermal equilibrium with each other. If two systems are in thermal equilibrium, there is a common property for that those two systems, which is the temperature. So if there is a net flow of heat from one system to another, the temperature difference between the two systems is responsible for this heat flow or thermal energy flow from one system to another. So that's all about the temperature. So temperature is the property which is responsible for the thermal equilibrium. So it determines whether a system is in thermal equilibrium with another system or not is the temperature. So that's all about the temperature from the zeroth law of thermodynamics. Thank you.